Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we're going to discuss about your Shannon-Fano coding. So these are the outlines. We're going to start up with the introduction where we will describe what we have studied so far. Then we're going to discuss about your Shannon-Fano coding, which will be followed by its encoding algorithm. Then we're going to discuss Shannon-Fano encoding example. And finally, we're going to conclude by discussing some of the Shannon-Fano encoding properties or Shannon-Fano codes properties. In our earlier lectures, we have studied about the basics of information theory, such as your average information content of BSS, entropy, average information in a message, information content, etc. We have also taken a look about the fundamentals of source coding, what is its requirement, and what we actually have to do in our source coding, that is to reduce out the redundancy. And now we're going to discuss various methods of variable length code generation, such as your Shannon-Fano coding. So it is one of your instantaneous code generation mechanism. So we just take a look what is Shannon-Fano coding, its algorithm, what does it says, and how we're going to code the information source with the help of Shannon-Fano algorithm. An efficient code can be obtained with the simple following algorithm, whose steps would have been given below. So Shannon-Fano algorithm states that the letter of the input alphabet must be arranged in order from most probable to the least probable. We had already discussed about your stationary sources, where that source will going to generate different sort of symbols, and the symbol generations or different symbols will going to independent with each other. That is, the occurrence of one symbol will not going to affect the occurrence of another symbol. So considering that particular thing into our mind, what we have to say that we will be having certain alphabets or symbols generated by our stationary source and several probability associated with the occurrence of each symbol. That is, different symbol that your stationary source will going to generate, several probabilities associated with that, that is known to us. So what we have to do is we have to arrange them in order from most probable to the least probable. That is, the symbol that your source will going to generate, the most probable one, or the probability of the symbol which is the highest, we have to align them first in our arrangement, and then less probable symbol, and we're going to keep continue that. Then the initial set of messages must be divided into two subsets whose total probabilities are as close as possible to being equal. Now when we have arranged the different symbols from their decreasing order of probability, then we have to make the partition, or we have to divide them into two subsets whose total probabilities are close to each other, or you could say being equal. Then all symbols have the first digit of their codes assigned. Symbols in the first set receive 0 and symbols in the second set receive 1. So in your first set we're going to assign as 0, and the second set, which is obviously the equiprobable, or which will going to be almost same probability of the second subset, then we're going to give that set as 1. Then the same process is repeated on those subset to determine successive digits of their codes, as long as any set with more than one member remain. So we have to keep continue this particular process till the time only last two symbols left. So when a subset has been to one symbol, this means the symbol's code is complete. So whatever we have discussed, let us understand with some example, so that all these algorithm steps must be clear to us in a much better way. So let us consider this particular example. Suppose we will be having a stationary source which will be going to generate these symbols, that is your x1, x2, x3, x4, x5, x6 and x7 as well as x8. So this particular stationary source will going to generate 8 symbols, and whose probability associated to the occurrence of each symbol is known to us. That is, for generating x1 symbol, the probability is 0.5. Similarly, for generation of x2 symbol, the probability is 0.25, and similarly for x8 we'll be having its probability of generation is 0.0625. So now in our first step, what we have to do is we have to arrange them in the descending order, or you could say the highest probability will going to comes first and the least probability will going to come into last. So if you closely observe that here in this particular question only, we'll be having this particular hierarchy order. that is given to us. So we just have write this ordered sequence, that is your x1, x2, x3, x4, x5, s6, x7 and x8. So where the probability of x1 is greater than or equal to x2, similarly probability of x2 is greater than or equal to x3, and same feature will going to be happen in all other symbols. So what we have to do is we have to divide our complete set into the two subsets where the summation of these two probabilities are almost equal. So summation of x1 and x2, if we closely observe that makes it 0.5, and rest of the sum is also equivalent to 0.5. So we have just make it two subsets. In first subset we'll be having x1 and x2 where the summation of all these probabilities is equivalent to 0.5, and second subset is your x3, x4, x5, s6, x7 and x8. And if you closely observe that the summation of all these probabilities associated with these symbols, that is also equal to 0.5. Then what we have to do is we have to assign one alphabet to one subset, that is 0, and we have to assign another bit 1 to this another subset. Then again we have to repeat out the same process. What we have to do is we have to convert this particular subset which consists of your x1, x2. We have again divided into two parts, that is your x1 and x2, and obviously the probability associated with your x1 is 0.5 and probability associated with your x2 is 0.25. So in this particular case they are equal, but it is not always be the case that the probability assignment is such that probability associated with your x1 and x2 they are actually equal. So we just have to make this condition true, that we have to divide them till the last step comes. So similarly in your second subset x3 and x4, this combination of this x3 and x4, that is 0.125 plus 0.125, that makes us 0.25, and again x5, x6, x7 and x8, the cumulative probability that will be equal to 0.25 only. So we have make this subdivision. Then again this particular subset is also going to contain two symbols, that is your x3 and x4, and this particular subset will going to contain four symbols, that is your x5, x6, x7 and x8. Then we have to again assign two single bits, that is 0 and 1 to these subsets. So that is your 0, 1 and again 0 and 1, and the actual branch and its root branch, the code associated with this complete subset x1, x2, that is your 0. So we have maintain this prefix 0, 0, that is common, and for this further subset x1 we have used this 0, and for this subset x2 we have used this symbol 1. In the similar manner, this 1 is for this complete subset, and when we are going to further subdivide into it, then we have to use this prefix 1 in both of the cases, and for one subset we have used this 0, and for this second subset we have used this 1. Then again we have to follow that particular process. So x3 and x4 will further divide it into x3 and x4, and similarly if we talk about this x5, x6, x7 and x8, so when we are going to sum up this x5 and x6, the probability is almost equivalent to your x7 and x8. Here most of the time I am using this word almost just because this is the general case, but in this particular specific example we are getting the case where all these probabilities are equal. So again we have to use the same coded pattern, that is for one subset we have to use 0 and for another subset we have to use this 1, and again the prefix we have to copy it down. So if we closely observe that, if we are talking about these two subsets, so here the root of this subset, the code associated with that subset is equal to 1 1, so we have applied this 1 1 as a prefix, and 1 1 also prefix to this particular subset also. And then for one subset we have used this 0, and for another subset we have used this 1. Then further again we have to apply the same process, that is x5 and x6. Again this particular subset will going to subdivide it into two symbols, that is your x5 and x6, and probabilities are equal. And similarly x7 and x8 also we have divided into two parts, that is your x7 and x8. Then again we have to use the same process, or you could say the method of assignment of code or bits associated with these subsets. So we have to use the same prefix thing, that is for x7 and x8, its root subset is this x7 x8, and the code associated with it is your 111. So we have used this 111 as a prefix for x8, and x7 also we have used the same prefix 111, and for x7 we have used this 0, and for x8 we have used this 1. In the similar fashion, for x5 and x6, the code associated with its root, that is equal to your 110, and we have again put this prefix 110 for x5 and 110 prefix for x6 also, and for x5 we have assigned this 0 and for x6 we have assigned this 1. So now we don't have any subset left, and if you closely observe that we had already obtained the individual coded values of different symbols or associated with the different symbols. That is, for x8 we'll be having this code word 1111, for x7 we will be having 1110, for x6 we will be having 1101, and for x5 we will be having 1100, and similarly for your x1 we will be having this 00, and for x2 we will be having 01, and for x3 we will be having 100, and for x4 we will be having 101. So if we closely observe that, we have actually find out distinguished codes corresponding to different symbols. So this is how we have to perform this Shannon-Fano coding. So in this particular table, we have formulated the same coded sequences. We have basically written the same coded sequences associated with individual symbol that we have obtained in the last slide with the help of your Shannon-Fano algorithm. So for symbol x1, probability associated is your 0.25 and the encoding vector, that is equal to 00. Similarly for x2, we have obtained this 01. For x3, we have obtained this 100. And similarly for x8 we have obtained this 1111. So all these are distinct instantaneous codes that we have obtained with the help of Shannon-Fano algorithm. Now if we have to obtain the entropy, or we have to calculate the entropy associated with that particular source, so the entropy formula is we had already studied, that is your minus pi log pi. So we have used this particular thing, that is minus times of 1 by 4 log of 1 by 4, and how many times we will be having this 0.25 probability or 1/4 of the probability, that is for symbol x1 as well as for symbol x2. So we have multiplied with this 2. Then plus 1 upon 8 log of 1 upon 8, and how many symbols will going to have this probability 1 upon 8, that is again 1 and 1, that is your 2. So we have multiplied with this 2, and similarly 4 times of 1 upon 16 log of 1 upon 16. So if we have evaluated the entropy, that would have been obtained as your 2.75. So you can just check it out whether we have obtained this 2.75 or not. So well, as of now, the answer to this particular source entropy, that is equal to 2.75 bits per symbol. So now when we're going to evaluate the average length of the encoding vector, that turns out to be, that is given with your L bar, that is equal to summation of p of xi ni, where ni is nothing but the number of bits used to encode that particular symbol. So that turns out to be 2 times of 1 upon 4, that is probability associated with your x1 and x2. In order to incorporate the probability of x1 and x2, we have multiplied it with this particular 2, and how many number of bits or ni we have used to encode those symbols x1 and x2, that is your 2, plus again 2 times of 1 upon 8, and how many number of bits we have used for that symbols, that is your 3. So 100, 101 plus again 4 times of 1 upon 16, and how many bits we have used to encode these symbols, that is your x5, x6, x7 and x8, 1 2 3 4 4 4 and 4. So 4 number of bits. So here that turns out to be 2.75. When we have evaluated that, that turns out to be 2.75. So average length of the encoded vector, that is also turns out to be your 2.75. So Shannon-Fano codes gives us 100% efficiency. So in this particular example, it has been cleared that your average information and your average length both are same. So we can say that in this particular case, Shannon-Fano gives us the 100% efficiency, or it is your 100% efficient code. So the Shannon-Fano gives the 100% efficiency since the average length of the encoding vector for this code is 2.75 bits, and it also gives the 0.25 bits per symbol compression, while the direct uniform binary encoding will be required 3 bits per symbol, which is redundant. So we could say that in comparison to uniform binary coding, we have compressed our source on an average by 0.25 bits per symbol, or we have basically saved 0.25 number of bits per symbol. So now we're going to discuss some of the properties associated with your Shannon-Fano. So Shannon-Fano coding is the most efficient when the probability of occurrence of each message letter xk is of the form of 2 to the power minus nk. So we have already seen in our last example also that is the case where the probability associated with your occurrence of each symbol, that is the type of 2 to the power minus nk, and summation k starts from 1 to n 2 to the power minus nk will be equal to 2 to the power minus n1 plus 2 to the power minus n2 plus up to the power minus nn, that is equal to 1. That is, we have also seen this particular summation thing in your Kraft inequality also. So a specific property in this particular Shannon-Fano encoding scheme is it will be most efficient one if the probability distribution is of this type. The prefix property always hold, and average code word length will be equal to summation k starts from 1 to n p of xk nk, where p of xk is the probability associated with your kth symbol, that will be equal to minus k is equal to 1 to n p of xk log base to p of xk. So where this particular thing log p of xk is basically referring your information, and this whole is basically representing the entropy, that is nothing but your minus pi log pi. So if this is the case where the probability distribution of each individual symbol is of the type of 2 to the power minus nk, then in that particular case the Shannon-Fano algorithm will going to gives us 100% efficiency. It should be taken into account that the Shannon-Fano code is not unique because it depends on the partitioning of the input sets of message, which in turn is not unique. We have also seen while discussing that particular example also that for one subset we are assigning value 0 and for another subset we are assigning 1. So if we just reverse the order, then we're going to obtain different sorts of codes. So if the successive equiprobable partitioning is not possible at all, but the example that we have seen where equiprobable partitioning is possible, as we have seen that most of the time when we have performed the partitioning, the probability of individual partition will going to remain same. So this is the special case where the probability distribution of the type of 2 to the power minus nk. So, but this is not always be the case. So the Shannon-Fano code may not be an optimum code. That is, a code leads to the lowest possible average length of the encoding vector. So it will going to gives us the 100% efficient code, or it would have been called as your optimum code when the probability distribution is of the type of 2 to the power minus nk. Then only it will be the most efficient case. And if this is not the case, I mean the probability distribution is different, then in that particular case it will not going to gives us 100% efficiency. So hopefully you have get the insight about the Shannon-Fano algorithm. That is how we will going to obtain the coded sequence for the different symbols generated by your information source. In case of any doubt, you can ask me in the comment section. I'll try to help you out as soon as possible. So these are the references. Thank you very much for your patient hearing.